Hey folks, Ms. Gosling here. In this video, you're going to learn about friction. By the end of the video, you'll be able to solve problems involving friction using the equation that the force of friction is equal to mu times the normal force. So let's go ahead and get started. And I want to start by introducing friction. So just to remind you, friction is any force that opposes changes or attempted changes to an object's motion. And I do want to specify that friction is also going to be parallel to a surface. So between the object and the surface. Now, when I say changes or attempted changes to an object's motion, what I mean is that frictional forces can make it hard to move an object, but they can also make it hard to start an object moving. So, for example, in this picture, you can see Barack Obama is trying to push this couch. The force of friction can stop him from pushing the couch, and then if he is able to start pushing the couch, the frictional force will make it harder for him to move it. So he can't just give it one push and let it go. Instead, with that frictional force, he is actually going to have to continue pushing the couch so that it continues to move. So that brings us to the equation for friction. So we define the force of friction, and through research we have found that the force of friction is equal to mu, which is our coefficient of friction, multiplied by the normal force. Now, one thing that's really cool about friction, or at least that I think is really cool about friction, is that the coefficient of friction mu is something that's figured out experimentally. So we can't actually use the chemical or physical nature of an object to figure out what its coefficient of friction is from first principles. Instead, what we have to do is actually rub two pieces of material together, change the mass of the object that we are moving so that we can change the normal force on that object, and use that to figure out what the coefficient of friction is between those two objects. So friction is cool because we have to actually do the kind of classic science experiments that you're used to doing for something like science fair to figure out what our coefficients of friction are. The last thing I want to do before I start solving problems with you guys is to talk about static versus kinetic friction. So as I mentioned previously, friction can make it hard to start an object moving, and then it also makes it forces us to continue pushing an object in order to have it keep moving. So it's the reason objects don't move on their own. So what's really interesting is that our coefficient of static friction, or mu sub s, is going to be different from our coefficient of kinetic friction. So what that means is that our coefficient of static friction, and so our force of friction for moving objects, is different than the force of friction on objects I'm trying to move, even though the materials are the same. And what's particularly interesting is that the coefficient of static friction is always going to be higher than the coefficient of kinetic friction. So what that means is that it's harder to start an object moving than it is to keep it moving once you've gotten it started. And this maybe makes some logical sense to you guys from what you've experienced in your life. So think about, for example, trying to push a heavy bookcase, or in our picture, trying to push a heavy couch. It's often easier to keep the couch moving than it is to get it started. So it may kind of feel like you have to really force the couch to get it to start moving, and then once you've got it moving, it's a little bit easier. You're putting in a lot less work. And that is because of this relationship here, that fact that the coefficient of static friction is going to be less than the coefficient of kinetic friction. Finally, I do want to mention that this means that for an object that isn't moving, the frictional force is always going to be less than or equal to the maximum coefficient of static friction times the normal force on the object. And this makes some sense too, right? So we don't want to talk about the coefficient of friction changing, but the frictional force when an object is not moving only needs to be large enough to balance out the forces trying to cause the object to move. It doesn't need to be any bigger than that, and so it won't be. Otherwise, the object would start accelerating in the other direction due to friction, and that's not really how friction works. So with that, let's go ahead and look at an example problem. When I apply a force of 3 newtons to a 5 Newton box, the box moves at a constant velocity. What is the coefficient of friction for the box? So the first thing that I can see is that my box is moving at a constant velocity. So that means that the net force acting on the box is 0 because it's in equilibrium. Now that I've done that, I am ready to go ahead and draw my free body diagram. So I am applying a force of 3 newtons to a 5 Newton box. So that means that the gravitational force on the box is 5 newtons and my applied force is 3 newtons. And I want to find the coefficient of friction for the box. And I know since the box is in equilibrium, there must be a normal force balancing out my gravitational force, and that there must be a frictional force in the horizontal direction balancing out my applied force. From here, I can go ahead and make my little table for x and y. In the x direction, I have my 3 Newton applied force, so in the positive direction, and I have my frictional force, which is going to be in the negative direction. And when I add those forces together, I should get that the net force in the x direction is 0. Similarly, in the y direction, I have my 5 Newton gravitational force, which is pointing down, so it's in the negative direction. And I have my normal force, which is going to be pointing up. And the sum of those forces, again, is going to be 0. Next, what I can do is I can solve in x and y for my frictional force and my normal force. So in the x direction, I have positive 3 newtons minus the force of friction equals 0. So what that means is that my frictional force must be negative 3 newtons. In the y direction, I similarly only have 2 forces, so that means that in the y direction, my normal force must have the same magnitude as my gravitational force, so my normal force must be 5 newtons. Now that I have my frictional force and my normal force, I can solve for my coefficient of friction, since I know that my frictional force is equal to my coefficient of friction mu times the normal force. Now, before I plug in numbers, one thing that I do want to caution all of you on, the equation that we use to relate friction and the normal force only tells me about the magnitude of those two forces. It does not tell me the direction. So what that means is that when I'm finding mu is always going to be a positive number. And when I plug in my force of friction and my normal force, I want to get rid of any signifiers of direction. So I don't need to have any positive or negative signs for my frictional force or my normal force, because I only care about the magnitude, the size of those forces. I don't care about the direction that they're pulling in. So that means that instead of writing negative 3 newtons for my frictional force, I'm just going to write positive 3 newtons, because again, we don't have any direction for our coefficient of friction. It is a directionless quantity, i.e. it's a scalar. So that means that our 3 newtons is equal to mu times our normal force, so mu times 5. Excuse me, and you'll notice I am putting in units here, because one thing that I want to do is I'm going to solve for mu by dividing by 5 newtons. And what I get is that mu is equal to 3/5 or 0.6. And you'll notice I don't have any units after mu. And the reason for that is that the frictional force and the normal force have the exact same unit. So those newtons are going to cancel out, leaving mu to be unitless. And mu is one of those interesting things in physics, one of the only things in physics that you're going to see where you don't have to give me a unit because it has none. So mu for this problem is 0.6. And just to reiterate, what I did was I followed all of the rules for solving an angled force problem. So I drew a free body diagram. I didn't have to break up angled forces, but I would do that if I had to. I summed my forces in x and y. And then what I did was I solved for FF and FN, and then I added an extra step of saying that my frictional force is equal to mu times my normal force to figure out what mu was. So it's kind of at that last step where I brought in my new friction equation. So let's go ahead, we've done an easier problem. Let's look at something a little bit more complicated. So in this case, I am rubbing a 5 Newton mechanical pencil with a piece of cloth and sticking it to a wall. The coefficient of friction between the pencil and the wall is 0.3, so this 0.3 is my mu. What is the magnitude of the electrostatic force acting on the pencil? So let's take a look, shall we? So I have my mechanical pencil stuck to a wall. I know that my mechanical pencil has a gravitational force acting on it of 0.5 newtons. And I know that there is an electrostatic force attracting my pencil to the wall. So what I'm doing here is, guys, is I'm picturing this is my pencil and it's stuck to a wall like this. So I have an electrical force pulling my pencil to the wall. And since my pencil, since my wall is vertical, that means that the normal force acting on my pencil is going to be pointing to the left instead of up, since it's perpendicular to my wall. Finally, I have a frictional force acting on my pencil, pulling it upwards, parallel to the wall, and resisting that change in motion that gravitational force would cause. So now that I've done this, I've drawn my free body diagram, I can again sum my forces up in x and in y. So in the x direction, I have my normal force, Fn, in the negative direction, and I have my electrostatic force in the positive direction. And when I add those together, I get that my net force is 0 newtons. In the y direction, I have my gravitational force of 0.5 newtons in the negative direction, and I have my frictional force acting in the positive direction. And when I add those together, I get that my net force is 0. So with this question, I'm being asked to find a mystery force, my electrostatic force, given only the gravitational force. So how do I do that? Well, I can use my gravitational force to find my frictional force, because I know that those two forces added together are equal to 0. Once I find my frictional force, so again, I'm going to go ahead and find my frictional force. Then I can use my F of force of friction equals mu times my normal force to find my normal force. And then finally, what I can do is I can use my net force in the y direction to find my missing electrostatic force. So let's go ahead and get started. First, I'm going to solve for my frictional force. And looking at my forces in the y direction, what I'll get is that my frictional force is equal to 0.5 newtons. Next, I can find my normal force, or at least the magnitude of my normal force, right? I've already figured out the direction. I know it's pointing in the negative direction. So let's go ahead and get started. So I know that my force of friction is equal to mu times my normal force. Thus, plugging my numbers in, I get that 0.5 is equal to 0.3 times my normal force. Dividing both sides by 0.3, I get that my normal force is equal to 1.7 newtons. Plugging that into the x direction and remembering to keep my sign still negative, since my equation tells me only the magnitude of my force, not its direction, what I get is that the negative 1.7 newtons plus my electrostatic force is equal to 0. Thus, my electrostatic force, F sub E, is equal to 1.7 newtons. And there you have it. That is the electrostatic force acting on my pencil. So we've done an easy problem, we've done a medium problem. Let's go ahead and look at an advanced problem. A modified Atwood machine is set up in which a mass M1 is pulled on a cart of mass 0.1 kilograms by a mass M2 equals 5 kilograms. The coefficient of friction between the cart and the ground is 0.1. The mass cart system is at rest. What is the mass of M1? So let's go ahead. We're going to draw a free body diagram for my mass M1, since that's where our friction is relevant. So I know that my mass M1 has a force of gravity acting on it, Fg. Next, I know that it's being pulled to the right by the gravitational force of mass 2. So I'm going to call that Fg2. This can be Fg1. Next, I know that there is a normal force acting on the cart. Let me go ahead and draw that in blue to keep my color code, my color scheme the same. My normal force is acting upwards. And I know that there's a frictional force resisting that pull from my second mass. So taking my whole nice picture and moving it up, what I will see is my nice, pretty looking, simple free body diagram for this problem. So let's go ahead and move forward to filling out our table for x and y. So in the x direction, the gravitational force of mass 2. So I'm going to call that again Fg2, or going ahead and putting in numbers. I know that Fg2 is equal to m2 times gravity, or 9.8 times 5. I'm going to go ahead and do that here. Thus, I have a force of positive 49 newtons pulling my cart to the right. And I know that my frictional force is going to pull my cart to the left for a net force of 0 in the x direction. In the y direction, I have my force of gravity on the cart, so Fg2. And and that's going to be acting in the negative direction. And I have my normal force balancing that out in the positive direction, giving me a net force, again, of 0 newtons in the y direction. And we're going to solve this problem much in the same way that we did the previous problem. So we're going to go ahead and solve for our force of friction, use that to find our normal force, and use our normal force to find our gravitational force in the y direction on our mass number 1, which I wrote as Fg2 instead accidentally. So let's go ahead and fix that right here. Okay, so let's go ahead and do that. So in the x direction, I have positive 49 newtons pulling me to the right, and that has to be balanced out by my frictional force, meaning that my frictional force must be negative 49 newtons. Using my equation, frictional force equals mu times the normal force. What I will get is that my normal force is equal to 49, remembering to take the absolute value of my frictional force, divided by mu, 0.1. Thus, my normal force is equal to 490 newtons. Let's go ahead and give that a little color coding. So I can plug that into my equation in the y direction. We know that we're pointing in the positive direction, so our normal force is pointing up. And so that means that my force of gravity on my first cart must be equal to negative 490 newtons. So that means its magnitude is 490 newtons. Now my gravitational force is going to equal 9.8 times the mass of the cart, which I'm going to call mc, plus the mass m1. And when I add those together and multiply by 9.8, that's going to give me my gravitational force of 490 newtons. Since my gravitational force, of course, is going to be the force of the mass, as well, the gravitational force on the mass and the cart together. So this means that when I plug my numbers in, I get that 9.8 is equal to 0.1 plus my mass m1, and all that is equal to 490. So what I get, dividing first both sides by 9.8, is that 0.1 plus m1 is equal to 50 newtons. And so m1 is equal to 49.9 kilograms. Oh, and I wrote newtons instead of kilograms. Excuse me, let's go ahead and fix that. So there you have it, guys. Here is example 3. One extra problem for you guys to take a look at using friction in a slightly more complex system. So that brings us to our takeaways. So first of all, friction resists changes in motion. Our coefficient of kinetic friction is always going to be less than our coefficient of static friction. It's easier to get something moving, to keep something moving, than it is to get it moving. And finally, it can be important to change our frame of reference from the standard XY plane to solve force problems. So with our modified Atwood machine, what we had to do was essentially treat this whole length of our string as kind of the X direction, even though that mass M2 is pointing down in the Y direction. Now, I do want to take this last moment at the end, just a quick bonus, why I can do that for my Atwood machine. So if I look again at that Atwood machine system where I had that mass M1 on a cart attached to a pulley, upon which I had M2 hanging down. And you'll notice when I did that question, what I did was I pretty quickly just kind of glossed over the fact that I have my gravitational force of my second mass down here as a force acting in the X direction on mass 1. And I do want to take the time to explain that. You guys do not have to have this in your notes. You're welcome to ignore it, but I think that it will improve your understanding of this material, so I recommend just taking the time to watch through this explanation. So if I look at the forces acting on mass 2, I know that mass 2, there is the gravitational force of mass 2 pulling down, and the force of tension of the force of tension between mass 1 and mass 2, stopping mass 2 from pulling up. So, stopping mass 2 from falling down. Now, I know that mass 2 is not moving, which means that the net force on mass 2 is equal to 0. So the tension force minus the gravitational force must be equal to 0. And my tension force must have the same magnitude as my gravitational force acting on mass 2. Now, looking at my first mass, M1, I know that there's the same tension force pulling on mass 1 as there is on mass 2. And I know this because I know that the force of one object on another must be equal to the force of, so the force of object 1 on object 2 must be equal to the force of object 2 on object 1. And you guys saw that in the lab with the spring scales. So what this means is that my force of tension pulling mass 1 to the right is equal to the force of tension stopping mass 2 from falling. Therefore, that tension force must be the same as the gravitational force on mass 2. Since it's balancing out mass 2, it's stopping mass 2 from falling. So there is your explanation for why I can use that tension force, or why I can use that gravitational force on mass 2, instead of talking about the tension force, to substitute for the tension force pulling mass 1 to the right. So with that, you now know how to solve both friction problems and some of our fun Atwood machine pulley problems. So with that, I'm going to let you go. Best of luck. Try some problems on your own. Happy solving.